Hello, everyone. Thanks for joining us today. Today we have Esraa. Esraa is a third-year PhD student at RLAI lab advised by Martha White. Her main research interests lie primarily in online reinforcement learning, real-time recurrent learning, and continual learning. She received her MSc in computer science from University of Alberta, where she worked on efficient real-time recurrent learning approaches for online reinforcement learning. Esraa, on to you. The floor is all yours. You can get started.
Okay, thank you. So today I will be talking about our recent paper, Deep Reinforcement Learning with Gradient Eligibility Traces. So a little bit of a disclaimer first. The number of equations on the slides will increase exponentially as we go through the talk. So if there is any question at any point, please feel free to interrupt me. And so I will start first by talking about the problem that we're trying to solve in this paper. So this is a typical reinforcement learning diagram. We have an agent interacting with an environment, and at each time step, the agent will perceive some state from the environment, and it will act with some action. And in response to this action, the environment will transition to a new state and give the agent some reward. And the agent goal basically is to find the policy, which is a way of behaving in the environment, such that it maximizes the rewards it gets. Basically, the agent wants to maximize this quantity, the expected sum of discounted future rewards, which looks like this. So this is the sum of all future rewards, and we discount them by discount factor gamma, which control how much do we care about immediate reward versus rewards in the far future. And as I said, the agent goal is to find this policy pi that maximizes this quantity. And while the agent is trying to find this policy, it usually ends up with this other policy, and it asks the question, how good is my policy? And this is an important question, because if you know how good is your policy, you can improve on it in the future, right? And this is basically the question that we're trying to answer here. How can the agent evaluate a policy? So this problem is called policy evaluation because you have a policy and you want to know how good it is. And it's also sometimes called value estimation. So how do we know if a policy is good? We usually estimate one or two quantities. So the first quantity is this V pi, which basically says if I follow this policy, starting from this state, how much rewards will I collect? And there is also another quantity, which is similar, but it's saying if I start from this state, take some action, and then follow the policy afterwards, how much rewards will I get? And if I know V pi or Q pi, I can say how good my policy is. So the talk will all be about this value estimation problem. Given some policy, how can we estimate V pi specifically? And the extension to Q pi is straightforward. Okay, so when we're thinking about solving this value estimation problem, we might think, what do we want in a solution method? So we want a stable solution. We want solution methods that don't diverge, basically. We also want them to converge to a good solution, because if you have a method that converges to a bad solution, then it's not that much better. And we also want them to work well with nonlinear function approximation. We want to be able to use neural network with them, and all the other things that needs nonlinear function approximation. We also want them to be computationally feasible, and we want them to work well in off-policy learning. So off-policy learning is this special case where you're trying to learn about a policy using data that was collected by a different policy. So it's a harder problem. And we also want these methods to have a fast credit assignment. And by fast credit assignment, I simply mean imagine you have this grid world where there is a +1 at the end and there is nothing else. And let's say the first time the agent see this +1, it took that trajectory. Most of the methods that we will talk about in a little bit will only update the value of this last state once you see the +1. And then you will need to see the +1 again in order to update this state, and so on. So you will need to see this +1 through that trajectory many times to be able to update the value of the states along that trajectory. And this is what I refer to as slow credit assignment, because it took you a while to propagate that +1 back to that trajectory. A fast credit assignment method will update the states, the value of the states across the whole trajectory the first time you see the +1. And of course, this will be good for sample efficiency. So we have a long list of characteristics that we want, and let's see what can we do with that. Okay, so we know the problem that we're trying to solve, which is this value estimation problem. And we also know what we want in a solution. And then the next question would be, what about the current solution methods? Do they achieve the things that we want in our solution? So I will start talking about one of the main solution methods that we all use and works usually really great, which is the semi-gradient TD methods. And so this is the VBI that we started with. This is the quantity that we want to estimate, but we don't have access to. And we will estimate it using this V hat. So V hat is our estimate of the value of the state, and it's parameterized by some parameters W. And we might think what we want is to minimize the error between VBI and V hat. Of course, we don't have access to VBI, but we will be in denial about that for a few minutes or a few seconds. Okay, so we want our estimate to be close to VBI. And we want to do that for all the states, not just one state. So we will sum over all states, and we will weight different states by some weighting. So maybe I care about some states more than other states, so I will give them different weightings. And this quantity is called value error. So this is the value error. We want to minimize this value error because if we minimize it, that means our estimate is close to VBI. So we can do gradient descent. So that will be our weight update. And then we can stop being in denial about this VBI thing and ask ourselves, okay, we don't have access to VBI. How are we going to estimate this weight update? And one thing to do is we can replace this VBI with something else. I'm calling it U. And we choose U in a way such that in expectation, it goes to VBI. And one of the famous targets that we can use is this one-step target, the reward plus gamma and the estimate of the value of the next state. And so we replaced this VBI with this one-step target, and now we have something that we can estimate. And this is probably, like, if you try to look at any RL algorithm, they are using this quantity a lot. And this is basically what we call the semi-gradient TD. And the reason I call it semi-gradient is, so this weight update, this gradient is only considering the gradient with the value estimate of the current state, right? And it's not considering the gradient of this component, even though this component also depends on W. So that's why these methods are called semi-gradient TD methods, because they are ignoring the gradient component here. And in most implementation, you would see them using stop gradient operation. This is basically to do this semi-gradient TD update. Okay, so semi-gradient TD methods are not true gradient methods because they are not taking the gradient of any objective function. And you might be wondering, okay, so what? They work super well. Almost all of the RL algorithms that we know are based on semi-gradient TD methods. But that's not fully true, because if we look at all of the RL problems, and then we can divide them into on-policy and off-policy methods, on-policy and off-policy problems. So on-policy problems where I'm trying to estimate the value of the policy I'm following, and off-policy is when I'm trying to estimate the value of some policy, but I'm following a different policy. And in both cases, I might be using linear function approximation, or I might be using nonlinear function approximation. And here I highlighted in red, those cases are cases where there is a divergence example for semi-gradient TD methods, which means that like semi-gradient TD methods are not stable in all of these cases, which is a lot of cases. But then you might be asking, how could that be? Like DeepRL seems to work great, which is true, but we usually have so many stabilization mechanisms in DeepRL. Things like replay buffers, target networks, clipping, and so many more. And those stabilization mechanisms kind of mitigate some of these divergence issues. But maybe we can step back and ask, can we actually find methods that don't have these stabilization issues? And maybe when we do that, we can get rid of some of the stabilization mechanisms that we use. So a small recap. So at this point, we know the problem that we're trying to solve, which is the value estimation. We know a list of things that we want in our solution. And then we started talking about the current solution methods, and we found that they have some stability issues, which is they are susceptible to divergence. So they kind of don't satisfy the first thing that we wanted in a solution method. So the follow-up question to that would be, okay, has anyone tried to solve these stability issues? And the answer is yes. And most of these approaches that try to solve the stability issues will ask this question. Maybe let's try to find an objective function and do normal gradient descent. And if we do that, we kind of are guaranteed to converge in the same sense that gradient descent converge. And then the question is now, what kind of objective functions we can use so that we can do gradient descent on them? So let's get back to the value error. So this is the equation that we have seen earlier. And a related objective function to this would be this Bellman error. So the Bellman error, basically, you can think of it as replacing this V pi with the one-step target, kind of similar to what we did. The difference is we have this expectation now. So the Bellman error is a nice objective. Maybe we can try and optimize it. So this is the Bellman error. And if we try to optimize it, okay, so what does that mean? Let's try to get the gradient of this objective with respect to W. That's what we do when we do gradient descent. And if we do that, so this is the part that depends on W. It's an expectation square. So if we try to get the gradient of this thing, it will look like this. It's a lengthy equation, but the important thing here is like we were trying to get the gradient of an expectation square, which is basically 2 times the expectation itself times the gradient of that expectation. And what we care about here is we have 2 expectations multiplied by each other, which is quite hard to estimate, because that means we will need 2 independent samples of this next state in order to have unbiased estimate of this quantity. And typically, we will not be able to get 2 independent samples of the next state. Maybe if we have a simulator, we can unroll back the simulator and get another sample of the next state. Or maybe if we have a deterministic environment, that could be a possibility. But typically, it's not feasible to have in 2 independent samples of the next state. And this is known as the double sampling issue with the Bellman error. Another issue is that there are some learnability issues with Bellman error. I'm not going to go into details with this learnability issues, but there is a very nice example in the RL book in chapter 11, I think, about how this Bellman error is not learnable from a stream of observations, which is a big problem when using this Bellman error as an objective function. Okay, so this Bellman error was interesting, but we have some issues with optimizing it. So maybe we can look for other objective functions. And before we look for other objective functions, we will do some geometry about this Bellman error. So we have this quantity, and we can call this quantity as, so this is kind of the Bellman error per one state, right? And then we weighted over all the states in the state space. So this delta bar is the error for one state, and then we can have a vector with the error for all states in the state space. And we can think of the Bellman error as basically taking the weighted mean of that vector. So if we try to plot this vector, before that, we can imagine that there is like a space of all functions that can map from states to real number. So any of those functions can be a potential value function, right? Because they can map from states to a real number. But of course, some of them will not be representable in the function class that we choose. And maybe some of them are not as interesting. But the important thing here is, depending on the function class that we choose, we might not be able to represent all possible functions, right? If I choose linear function approximation, there will be some functions that I will not be able to represent, and so on. Okay, so the space of function that we can represent f will be smaller than the space of all possible functions f all. So if we imagine that this is our space of functions that we can represent, then maybe our v by that we're trying to find is outside that space. So we can project it to our space. And then maybe so the value that my estimate of the values will be lying in my space of functions. And then if I look at the Bellman error vector, it will look like this because it's sticking out of the space. And one thing we can do is we can project it back to our space. And then we would have this error. So this error is called the projected Bellman error. So it's the error after I project this Bellman error vector back into the space of functions I can represent. So this is the projected Bellman error. Like, we took this error vector, we projected it back to our space that we can represent, and then we get a weighted norm for that vector. So this seems like a nice objective function, because now that we're constrained in the space of functions that we can represent, maybe we're able to find some good solutions. So the methods that try to optimize this objective functions are called gradient TD methods. And gradient TD methods are not new, they are quite old. But most of the development for gradient TD methods were done in the linear function approximation case. So they were first introduced in this paper, and then they were extended to use lambda returns. So lambda returns allow us to do the fast credit assignment I mentioned earlier. And there were some attempts to extend them to nonlinear function approximation here in this paper, but those attempts have some assumptions about the ability to do some linearization for the objective function. And they haven't been really used in deep RL. Okay, so this projected Bellman error objective, it's a stable because like we can take the gradient of it, we can do gradient descent, and then we're guaranteed to converge in a similar sense to how gradient descent converge. And they have been shown to converge to a good solution. So they have the good solution quality. The nonlinear function approximation cases is still not worked out yet. They are computationally feasible. They can work in off-policy learning. But there were some development for the fast credit assignment in the linear function approximation, but in the nonlinear function approximation, that part doesn't exist. So we're gonna focus on these two. So like it looks like we have most of the things that we want, but we're missing the nonlinear function approximation part and we're missing the fast credit assignment part. So in the next few slides, I will focus more on this part, the nonlinear function approximation, and then move on to this later. So let's go back to this Bellman error. And I basically replaced this part, So I basically replaced this part with this TD error, just for simplicity. So this is the expectation of the TD error squared. And one note from convex optimization is if we have a function square, we can replace it with this quantity. And if you're not familiar with this quantity, that's okay. I will have some intuition about it in the next slide. But basically what we can do is, this is a squared function, this is a squared function, so we're gonna use this equation. And we will end up with this. So let's get back to this part first. So this is a really nice equation in convex optimization. Imagine that we have a squared function. And I told you I don't want to use this squared function. Because if you remember, we don't want to use this squared function because it results in the double sampling issue, right? So I gave you a squared function and I told you I don't want to use this squared function, find something different for me. So what can we do? Maybe we have this point and I want to know if I give you an input of 2, what output you will give me. So if I use this function, the output will be 4, but I don't want to use this function. I want to use something else. So that other thing could be the tangent line at this point. So both the function and the tangent line will have the same output at this point. And the tangent line is basically, it's a line. It has a slope and an intercept. And if you solve for this slope and intercept, you will find them to be like 2h and minus h squared. So that line has a slope of 4, and then intercept will be minus 4. Okay, so I don't want to use the x squared. I can use this tangent line to estimate this point. So this is good. And we can do this for all the points on this function. So we can have all the tangent lines at different points. And whenever I give you an input, you just go to the tangent line corresponding to that input and evaluate the tangent line. And then we don't need to use this x squared anymore. And then the question becomes, okay, there are so many tangent lines now. How do I know which one corresponds to the point that I want? And this is where this equation comes from. So this is the equation for any tangent line. And once you pick an h, you pick one of those lines. And if I give you an input, so maybe I give you an input 2, and you want to know which of those tangent lines correspond to this one. It turns out that it's always the tangent line that will give you the maximum value. So here at this point, you can see that this green tangent line is above all other lines. And if you go here, you'll see that this black tangent line is also above other lines. And this is where the max comes from. So it's basically look at all the tangent lines, pick the one that gives you the max value. This is the correct tangent line. Okay, so why do we care about this part? Is, as I said, now we don't need to use this x squared anymore. We can use this equation instead. And what this equation gave us is that it removed that square. Because that square before, that was the reason we had the double sampling issue with Bellman error. So let's go back to the actual Bellman error and use this equation. So now we replace that expectation square with this max, and that's basically the slope, and that's the intercept. And our x here is the x1 expectation. There is no square now. And there is a nice result that we can exchange the max and the summation. So we can get this max outside, but the cost for that is here for each state, we were doing this operation. So once we get this max out, we need this, this max is now, we will have a specific h for each state, basically. So the h here was a number that let us determine the slope and the intercept. But once we get it out here, it ends up being a function of the state. So for each state, I want to find that number, basically. So h is now a function that maps from states to real number. And the ideal h, the optimal one, will be the one that that's equal to the expectation of the TD error. Okay, so we now have this new formulation of the Bellman error, and this delta is the one-step TD error, and all is good. But we have one more problem, which is that this h can be any function, right? So we will need to restrict h in the same way that we did before. So I will choose a class of function. I'm calling it h here, big H. So I'm going to use a class of function to represent this h, which means that, of course, not all the functions here I will be able to represent. And this is what we call the generalized projected Bellman error. And depending on the choice of function class, we can recover other objective functions. So if I choose my function class here to be linear function approximation, or a linear function space, then we can recover the linear projected Bellman error that I talked about earlier. But also there is no restriction here because I can choose my function class to be nonlinear function space. And this is the interesting part here. So with this objective, we kind of got rid of two issues we had before. With this reformulation, we got rid of the expectation square, which was causing us some issues. And now we have this h, which can be anything. It could be linear functions approximation. It could be nonlinear function. We don't have an issue with what h could be. So that's good. And at this point, this is kind of like the space of methods that we have. So this generalized projected Bellman error was developed for the one-step methods in both linear function approximation and nonlinear function approximation. But it wasn't extended to this lambda return thing, which would allow us to do the fast credit assignment. And this is basically the main contribution of our paper, is how can we extend this objective function to use this lambda return. So we now have an objective function that kind of achieve most of the things that we want, except for this fast credit assignment part. So the next part of the presentation will be about this lambda return and the fast credit assignment part. Is there any questions so far? Yes.
If you could just go back for a moment to the last difficult equation that you put up.
Yeah.
Could you just briefly comment on how exactly this equation solves the non-linearity problem?
Yeah. So here,
I'm a little lost, and if you can put me in the right frame of mind here, what exactly was H, here?
Okay.
Where are we
Yeah,
getting
that's okay.
H from?
Okay, let's look back at this here. Okay, so we had a problem with the Bellman error, right? Maybe let's look at the problem that we had earlier. I'll go back. Okay, so we had this problem, which is we had an expectation square, and then when we try to get the gradient of that, it ends up being this two expectations multiplied by each other, right? So we had this problem, and we wanted to solve this problem. One thing we can do is we want to get rid of this square, basically. Because if we get rid of this square, we will not have two expectations when we take the gradient. And then the question becomes, how can we get rid of this square? So that's why we talk a little bit of a detour. Sorry. Okay. So that's why we talk this a little bit of a detour. If we have just a function, a squared function, right? Anything. And we don't want to use this squared function. We want to use something else. But we want that other thing to give the same output as this squared function. And it turns out that this tangent line can give us what we want. So if I want to evaluate this point 2 using the squared function, so I give the squared function 2, it will give me 4, all right? And also this tangent line, if I give it 2, it will also give me 4, because both the tangent line and the squared function have the same point. And this is basically the equation of the tangent line.
Yeah. This part is okay. It's just that I probably need to look at the equation a bit more in order to be able to connect this H to what's going on in the more difficult looking equation. I apologize about this. I'm just not thinking. I'm just not thinking fast enough to be able to connect what's going on here to exactly how it relates to the RL equation that you put up. I probably should just look at it a bit more.
That's okay. So I think if you agree with this part, you agree with this part, right?
Yeah. Well, this is
okay.
This is okay. Yeah, sure.
Okay, then let's see how did I use it in this scary looking equation. I think it was. So basically here we had an expectation square, right? So I just like removed everything inside the expectation and added delta. So it's a smaller equation. So we have this squared thing, and this is basically like the x square, right? So we're gonna remove that squared part and use this equation instead. So our x here is this smaller expectation. And h is determine which tangent line do we use. So that's basically what happened here. So this x square is this part square, and we remove that square and we use this equation instead. And then the other thing is this max. So for each state, I need to solve this equation, right? Because we have a sum here over state. So for each state, I need to find an h that determines the slope of the line that I want. And what we do later is, so this is the same equation. What we do is we can get this max outside, but we will need to define an h for each state, right? So now h becomes a function of the state. So for each state, I will have this function that takes the state and gives me h, where h determines the slope and intercept of the line I mentioned earlier.
So this, okay, so this has to be learned we are going to learn this
Exactly.
during the learning process.
Yeah, exactly.
Oh.
Exactly. We will learn it. We will learn H.
Thank you very much. Okay.
Okay.
I appreciate that.
Okay. Yeah. Okay. And then the next step is, so now that this H, that's a function now, it could be any function, right? And some of those functions might be outside of the function class I can represent. So what we will do is we will just restrict H to be within a specific function class. So maybe I use neural network to learn H, then my function class is the function space that can be represented by this neural network. And depending on the choice, so if I choose H to be linear function space, we can recover all the gradient TD methods. And if we use H to be nonlinear function space, we don't have a problem. Okay. So the next part will be a little bit different, because so now we have this objective function, but this objective function is dependent on this one-step TD error. So in the next part of the presentation, we will see different ways to allow us to do fast credit assignment, because this one-step TD error will not allow us to do the fast credit assignment. So if there are other questions about this part, then this is a good point. Okay, if there are no other questions, I will go. Okay, so now we can ask a slightly different question. So we have the objective function, and now we're gonna ask how can we do this fast credit assignment. And we can imagine, so imagine that you are this person and you're at some state ST. And imagine that you have this superpower where you can look into the future. So if I can look into the future, what can I do? I can look one step ahead and then have this one-step target that we have been using so far. But I can also do other things if I can look into the future. I can maybe look 2 steps. So I will take the reward, discount the next reward, and then bootstrap from this value. But I can also do other things. I can look 3 steps, 4 steps. I can look as many n steps in the future as I want. And all of these are possible targets that we can use. But there is also another interesting target, which is maybe I look at all of those and I average them together. And this target is called this lambda return. So this GT lambda is our lambda return target, which will look into the future, look at all the future rewards and states that I visit, calculate all possible n-step return, and average all of those together. So when I assume that we can look into the future and look at other things, this is called the forward view. And then once we can get this target, that we now have a superpower that we can look into the future. So we get this target, and then we can try to make our value go to this target instead of just going to the one-step target that we have been using so far. So this is the forward view where we imagine that we have access to the future. There is an equivalent backward view, which is, by equivalent, I mean mathematically equivalent, which says, like, actually, instead of looking into the future, you can actually look back. So you don't need to wait until you see all of those things. You can accumulate some information about the past, and those information will allow you to compute the same quantity, basically. So we will look at the forward view first, and then we will get to the backward view. So this is the scary equation from before. And what I will do now is I will replace this delta, which was the one-step TD error. I will replace it with this delta lambda. such that this delta lambda is basically trying to make my estimate of the value closer to this lambda return quantity that we introduced. And so we will be learning this value, and we will also be learning this h, as we said a few minutes ago. So we have two things to learn. And when we're learning this value, we want to minimize this error, right? So we will do like gradient descent step here. But when we're learning this h, we want to do a maximization. So we will basically do gradient ascent instead. And in the following, I will present our updates as this. So the first update will be to minimize this, and the second update will be to maximize this quantity. Okay, so what remains now is we have this objective function. We don't have restriction on what h could be. So this could be a neural network or linear function approximation or whatever we want. We also don't have restriction on what v could be. So all what remains now is take the gradient of that thing, basically. So when we take the gradient of that thing, we will have our delta w and delta theta. Okay, so this is the equation. And first, we want to get the gradient with respect to w, and w only exists inside this thing. So when we take the gradient, that's the part that we care about. So it will have the gradient of expectation. And you can see here, because this is now only an expectation, it's not an expectation square as before, we don't have this double sampling issue. And then if we want to take the gradient with respect to theta, h is the only component that depends on theta. So we take the gradient of this thing, and it will end up looking like this. So this is the gradient with respect to w, this is the gradient with respect to theta. And of course, we can't really estimate this summation over all the state space, so we will use samples of that. And that will basically be our algorithm. So when we see a state, that's one sample of this gradient, and we will make an update using this sample. And you might be wondering about this gradient part. It looks a little bit scary, but this gradient part is actually very easy to compute. So as a reminder, this part was basically this lambda return minus our value estimate. And if you're familiar with algorithms like PPO, this term is usually called generalized advantage estimate. And it's basically a sum of all future TD errors. And if we write it like this, we can estimate the gradient easily, because like we can see that the gradient will have this recursive equation. Okay, so we had an objective function, we took the gradient, and that's our first algorithm, basically. And another thing is we can do, so we know that the optimal H star will basically be an expectation of this delta lambda. So the optimal H star is the H that we're trying to learn. And if we solve the equation like analytically, we know that it will be this expectation. So we can use this fact to bias our algorithm. And by that, I mean, like I took the same thing I had here and I added this additional term. So since H is trying to approximate this component, once we reach to this optimal H star, this thing will be 0. And this term basically is trying to make H hat closer to delta lambda as possible. So it kind of biases the update so that we converge faster. And we don't do anything with the theta. So that's the second algorithm. And then finally, so our final algorithm will take the same update from here, but it will change the theta update. It will add this regularization term. And this regularization term is interesting because it allows us to move between those gradient updates and the semi-gradient TD methods that I talked about earlier in the presentation. So this beta thing can be between 0 and infinity. If beta is 0, so we will basically get rid of that term and we go back to this algorithm, which is our gradient TD update. And if beta goes to infinity, that means theta goes to 0. And if theta goes to 0, we get rid of those terms. Theta is the parameter for h, right? So we get rid of h, basically. And when we do that, we go back to the semi-gradient methods. So this beta allows us to move between these two types of algorithms, basically. And this TDRC will end up being our main algorithm since it has all the components in it. So the next step is, let's use this algorithm. And the method I developed so far is based on the forward view that assumes that we can look into the future. And while we can't look into the future, usually if we have a replay buffer, we can pretend that we can look into the future to some extent. So this is basically similar to what PPO does. So a quick recap of PPO, which is a policy gradient algorithm, is you basically collect a trajectory, and then you split this trajectory into many batches, and then you update your value estimates towards the lambda return. But PPO would do this semi-gradient update, like you will do like a stop gradient around here. And after you compute your value update, you can update your policy and repeat. So we will basically do the same thing, except that we will replace this component with our objective. And we will keep everything in PPO the same. So this is the main part that changed. And when we see how did this perform, we will see, so here's 4 environments from MuJoCo. So we have PPO in red, and we have gradient PPO, which is our algorithm that's basically use PPO for everything except for the value estimates. It will use our updates. And in 2 out of the 4 environment, it achieves a better performance. And even here, it's similar to PPO, which is good because like we know that this algorithm kind of maps between the semi-gradient methods and the gradient method. So that's good results. Okay, so that was the forward view where we assume that we can look into the future a little bit. But we can develop this other view, which is the backward view. So the backward view will assume that we can't look into the future. All what we can do is we can see what happened so far. And we have this theorem that says you can actually make the same update that you did in the forward view in this backward view, where you don't look into the future. So these 2 parts are basically the updates we had from before. And we can see that if I keep doing those updates, there is an equivalent form for those updates. These two forms. And what's interesting about these 2 forms is they depend on these 2 components, these 2 new things. Everything else, like we know. So this is the one-step TD error. This is the H. This is the gradient of H. And we have these additional 2 new things. And those things are basically carrying information from the past. So this ZH is carrying information about H, and this Z theta is carrying information about the gradient of H. And what we show is if you do updates using these 2 components, we call them traces because they kind of have a trace of the past. If you do the updates with these components instead of these, you will end up with the same weight updates. So the algorithm ends up looking like this. We keep track of those traces and we use them to update our weights. And we can also develop another algorithm that does this biasing thing I mentioned earlier. And I know it looks scary, but what we want to see from this equation is we can actually write this update as 3 terms. This first term is actually the same term that you would get from a semi-gradient method. And this term, we call it an instantaneous correction. And this term is basically our gradient TD lambda. So we can also do updates using these terms, and we get to our final algorithm again, which will just have this additional term. And this is the same regularization that would allow us to move between gradient methods and semi-gradient methods. Okay, I know that this last part is has been a lot of equations, but basically the main point here is we have this forward view where we look into the future, and we have this equivalent backward view where we don't look into the future, we just use information up to the current time step. And we show that if you do this backward view, you end up with the same updates. And we have this algorithm, QRC lambda. So QRC lambda is based on Q-learning, but it adds this gradient component, and it adds this lambda return component, and it does this backward view updates. So the algorithm goes like this. Like if you compute your one-step TD error, you compute the gradient of that, and then you have this trace of H values, you have this trace of gradient of H, and you also have this additional trace of gradient Q. And you use those traces to update your parameters W and theta. And the nice thing here is if you look at any of the indices I have, they are all either T or T minus 1, or T plus 1 for the next state. But that's it. Like we don't have any future time steps that we're waiting for, which means that we can use those updates at every time step. So once I see my next state, I can make an update. So I don't need to wait to the future. I don't need to have a replay buffer. Yeah, that's the interesting thing about this algorithm. And we evaluate this algorithm on MinAtar, which is a small version of some of the Atari environments. And our algorithm, this QRC lambda, is in blue, and it performs really well in all of these environments. We have 2 baselines here. So Q lambda is like the semi-gradient version that will, this is basically the old Q lambda. And StreamQ is also another algorithm that doesn't need a replay buffer. And our algorithm basically outperforms these 2 in all of the environments. And so the main takeaway from all of this is semi-gradient TD methods that we all use and love, they are susceptible to divergence. And while we can add a lot of stabilization mechanisms, it's a good idea to step back and try to think, how can we develop more rigorous algorithms that need less stabilization mechanisms, or hopefully no stabilization mechanisms at all. And that comes from the gradient TD methods, but the gradient TD methods were mostly used in like linear function approximation, or with this one-step TD error that doesn't allow us to do fast credit assignment. And the main contribution of our paper was basically to extend gradient TD methods so that we can use this lambda return, which allow us to do fast credit assignment. And when we use this lambda return, we can have the forward view or the backward view, where we can either assume that we can look into the future, which is something that we can partially do if we have a replay buffer, or we have this backward view, methods that don't assume we need to look into the future. They don't need to have a replay buffer. And we develop methods that could be used in both cases. Yeah, and that's the end of my talk. So if you have any questions, and I hope that wasn't too annoying.
Yeah, it was a great session. Thanks for trying. Thanks for presenting. Yeah, I hope you're okay to take questions offline. If any of
Yeah.
you guys have questions, you know.
Yeah, of course. Like if there are any questions, like feel free to reach out. I would be happy to answer any questions.
Yeah. Thank you. Thank you.
Thank you.